All right, so where we left off on Wednesday is we were discussing this closed-loop discrete communication prosthesis. And I just want to remind you of the task. So we have a monkey here, and he is holding a center target, shown right here with his hand. And what we've done is we've cued a little green square in this area right here, and he's planning to reach towards that target. As he is planning this activity, what we're doing is through this electrode array that we've implanted into his primary motor cortex and premotor cortex. And so you remember these regions are primary motor cortex, PMD, and M1. And PMD was responsible more for plan activity. It has movement activity also, but it has more plan activity. And M1 has a tiny bit of plan activity, but it's more responsible for movement activity. We recorded our raw voltage waveforms from these areas of cortex. We spike sorted, and then we passed it through a decoder algorithm, this block right here, to decode his intended target, which we showed as a blue circle around the desired target. And so this was the whole task that we had set up, and we had talked about the signals, what we're recording. And what we're really going to get to now in the rest of this talk is how we build this block, the decoder. And this is also going to be a large part of your homework 3. Homework 3 will be building these decoders to decode the plan activity. All right, so as we mentioned before, for communication prostheses, what we care about is ultimately a bit rate, an information communication rate. And so this is something that has units of bits per second. And you guys all know this very well. When you download a file, it'll say that it's downloading at, say, 1 megabyte per second. And so for these communication tasks, the bit rates are a lot lower. We're going to end up seeing bit rates on the order of maybe 5 bits per second, right? And this is less than 1 byte per second. A byte is 8 bits. And so it's a lot less than a kilobyte per second, which were your download speeds when you were on dial-up modem. Anyways, we're going to want to optimize this bit rate, which is our performance metric. And this bit rate is a function of 3 main variables. The first variable is task difficulty. And so by task difficulty, what we mean is basically how many targets are there. And this makes sense because if we have just 2 targets, so let's say we have target 1 and target 2, how many bits of information can we convey with one selection? Yeah, I saw some people math it. You can convey 1 bit, right? One of these is 0, and one of these is 1. And if you had 4 targets, then you can convey 2 bits, 0, 0, 0, 1, 1, 0, and 1, 1. And so in general, if you have n targets, how many bits can you convey? So we know that if you want to convey, for example, 3 bits, you'll need to encode 0 and 1. So that's 2 different numbers in 3 different ways. And so you would need 8 targets to convey 3 bits. And that makes sense. If I write out all the permutations of 0, 0, 0, 0, 1, 0, 0, 1, et cetera, then you would have 8 of those. And so in general, if you have n targets, then the number of bits that you convey is log base 2 of n. Does that all make sense? All right. And so the first thing that we care about in measuring performance is the task difficulty. The harder the task, the more bits you'll be able to convey per selection. And so if you make the task more difficult, then as long as your accuracy stays high, you will increase the number of bits that you convey per second. And so that gets us to the second variable, which is accuracy. And for accuracy, this is just a fraction of targets that you select correctly. And so if you had, for example, 16 targets, then each selection would convey 4 bits. But it's easier to decode 1 of 2 than 1 of 16, right? If you have 16 targets, then the targets will, for example, be more closely spaced to each other. And so if you had targets lined up around a circle, 5, 6, 7, 8, and then you all of a sudden made it doubly as dense, and so you put targets in between, you would make more errors because if you wanted to decode, say, this target, you might accidentally decode this one or this one. The neural activity decoding those targets will look similar. And so if you increase the task difficulty, that's great for transmitting information, but it might, at the same time, lower your accuracy. And if you lower your accuracy, you make incorrect selections. Those incorrect selections don't count as transmitted information. In fact, sometimes those incorrect selections hurt you, right? Because if you're typing on your keyboard and you hit a wrong key, then what do you have to do? You have to hit the backspace button, right? And so all of a sudden, you have to make 2 selections to convey a net of 0 information, right? So if I type THE and I type instead THF, and then I hit the backspace key, now I've made 4 hits, but only conveyed T and H. And so your accuracy wants to be high. And so there's this trade-off between task difficulty and accuracy. The last variable that we care about is the speed of the decoder. And so this should also make intuitive sense. If you're making selections at a quicker rate, you're going to increase your bit rate because you're transmitting more correct selections per unit time. Do these 3 variables make sense to everyone? Any questions on them? All right. All right, so one of the things that we're going to care about now, given that we know that our goal is to optimize bit rate, is how much time does it take for each selection? What's the speed? This is the second variable. What's the speed at which we can make selections? And so here we're just going to, in much detail, diagram out the task. And this is the same data that you'll be working with on homework 3. And so we have a monkey. He starts the task by acquiring a center target and also fixing his eye. While he is acquiring this target, we'll know that he's engaged in the task. At that point, what we'll do is we'll then queue a target at some location, for in this case down here. At this point, the monkey begins to plan to that target. And what we do is we record his plan activity, and then we pass it through a decoder, and we say, you meant to select this target. And if it was wrong, we would say, for example, you meant to select this target, and that would be an incorrect selection. In this case, it's shown to be correct. And so there are a few variables of interest here. So the moment when he touches and acquires the center target is this time right here. Now, after that time, there's this time t/pht, which you guys will not have to worry about. It's just a time at the beginning of the trial before we actually queue the target. But when we queue the target right here, that corresponds to this time. And there are 3 then time variables that we care about, but only really 2 that we control. So the first is t-skip. And so t-skip right here corresponds to the time after we've queued the target and before we start to integrate the neural data to decode an intended reach to that target. And so why do we have the skip time? Well, we know from our last lecture that when we show the target, there's this latency for the target's visual, for the visual information to go into your brain, to be transformed, to be sent to the motor cortex, and then for you to start to form a plan to that target. And so the next slide will show how we select this t-skip, but this t-skip is basically, you can think of it as reaction time. If I were to show you a target right now, for the first, say, 150 milliseconds, you wouldn't have had time yet to plan a reach to that target. And so this t-skip is basically accounting for reaction time. And more formally, it's the visual latency and the time it takes for you to actually pick out that target and then select a plan to it. Then after that, after this t-skip, we would think that the activity, and this is the case, the neural activity in the monkey's brain is now reflecting the intent to plant this target. And so this epoch we skipped. But then this epoch is good data that we actually want to integrate and we want to use to decode the prosthetic reach that we have here. And so this variable tint is some window that we can sweep. And we'll see this later, but there's some obvious intuition on how to pick tint, right? If tint is longer, we integrate data for longer. If we integrate data for longer, we can make a more reliable decode. But if tint is longer, then we're slowing down the speed of our prosthesis. And so there's a speed accuracy trade-off in picking tint. And then finally, there's this last time, t decode plus rend, which is just some time that's fixed in the tasks. And so it takes us some time to actually decode the data that we've integrated in tint, and then to show that decode to the monkey. And that time ends up being about 20 milliseconds. Any questions on the timing of the task? All right. So the first thing that we want to set is t-skip. And so for t-skip, and I want you to ignore the red line for now. Oh, Anjali?
What was it? 10 milliseconds after that?
Oh, yeah. So then after we show the target, there's just some latency for us to send the juice command. And so that's the 10 millisecond latency that you see there. And then after the 10 milliseconds, the monkey will get juice. So in the end, really the only times that we'll care about and the only times that you'll play with on your homework are these two times here, t-skip and t-int. All right, so ignoring the red curve for now, one way in which we can choose t-skip is to just empirically measure what our accuracy is for various values of t-skip. And so what they did in the lab, what Gopal and Stephen, the first authors on this paper, that was the required reading for this lecture, did in the lab, was they set up this distractor task where they have 8 different targets. And so those are these targets right here. And then they prompt just one target. The distractor task is more reasonable for a real-world setting because when you're typing on a keyboard, you obviously have distractors. You're not just planning a reach to one target, but you have all 26 keys on the keyboard or 26 letters in the alphabet to choose from. And so these act as quote-unquote distractors. And so in this experiment, they set up all these distractors, and then they prompted one target. And then they said, OK, I'm going to start integrating, for example, a t-skip of 0 for 200 milliseconds. And I'm going to see what my decode accuracy is. And so if they started at time 0, they would find that the decode accuracy is not significantly higher than chance. So chance is 0.125 because there are 8 potential targets, and you're just selecting one of those 8. And so if we start counting from time 0, then obviously the information, if our decode is not better than chance, isn't really meaningful information, right? So in these first 150 milliseconds, you have information coming into you about the distractor targets, about the target that you want to plan. And what you have to do is you have to pick out this target out of the distractors and then make a plan to that. And so then they made t-skip 50 and saw the performance was still not above chance. But as soon as they got to t-skip of 150, if they started to integrate from here, we saw that the performance began to plateau. And so this is the justification that they use for choosing a t-skip of 150. And this sort of corresponds also to reaction time. And so that's how we decided to jettison the first 150 milliseconds of data. Does that all make sense? Any questions on this slide? All right. All right, and so now that we have t-skip set, and that's just skipping the first 150 milliseconds of data because during that time the monkey has not yet formed a plan, now we can set tint. And so this is a plot that you're actually going to replicate, or not replicate, but make on your homework. And so what Gopal and Stephen then did is on an experimental day, they swept this tint here on the x-axis. And so we've already accounted for t-skip. And so after t-skip, we're plotting here on the x-axis how much time you spent to integrate. And across all 4 days, they saw the intuitive result, which is as you increase tint here, your accuracy increases. And then this makes sense because when you increase tint, you get a better measure of the neuron's firing rate, right? If we remember from the firing rate statistics lecture that if you want to calculate that average firing rate, R of t, or just R, if you have more data, if you can bin the data in a longer bin, then you can help to reduce some of that noise that is occurring in your spiking, in your spike rasters. And so when you integrate data for more, you basically get a better measure of the average firing rate, and you're able to decode better. Whereas if you only integrate data for 50 milliseconds, you're receiving spikes there, but those spikes could be really noisy. And so if you try to decode off of this very small window of data, then you would have a pretty poor accuracy. And so this is sort of hinting already at what the optimal tint should be. And so based off of these plots, would I ever want to set tint to be 400 milliseconds? Who says yes? Who says no? All right, and what's the main reason why? Yeah, exactly. So you could integrate for just 200 milliseconds right here, and you have basically the same accuracy as 400 milliseconds. And so in this case, what you've done is you've decreased your integration time by half for the same accuracy. And so basically, when this plateaus, there's no way in which you would want to integrate more data, because then all you're doing is slowing down your system. The really interesting question gets at, do we pick a tint of 200 milliseconds, or do we end up coming down to this area here and only have a tint of 50? And this isn't immediately as clear because let's say at tint of 50, we had 60% accuracy. And at tint of 200, we had, what was that, 95% accuracy. So it looks like we got a pretty big boost in accuracy here, right? But then what we've done is, if you remember, we set t-skip equals 150, and t-decode plus render is equal to 40. I'm just going to call this 200, even though it's 190. For sake of simplicity. And so if we integrate for a tint of 50, then the time for each trial is 250 milliseconds. But if we integrate for a tint of 200, the time for each trial is 400 milliseconds. And so we've almost doubled the time it takes to make each selection, but we've also gotten a 35% increase in accuracy. And so how do these two trade off? So what we could do is we could perform an offline simulation or a simulation on the data that we've already collected and calculate what the theoretical achieved bit rate you could get is based off of these accuracy and speeds. And so on the x-axis, what we're showing is the t-skip plus tint plus decode plus rend. So this is just the time it takes to make a selection. And on the y-axis, we're plotting what we just saw before, which is the accuracy. And so if we now plot on the y-axis bits per second, which, if you recall, is the variable that we care about, right? Bits per second is a measure of the information you can transmit per unit time. And we always just want that to be as high as possible. Then it turns out that your optimal is actually in this region where your tint was relatively low, but your accuracy, your tint was relatively low and your accuracy was also low. It turns out that being faster, in this case, was better than being more accurate. And so you can think of if you're typing, if you're on your iPhone, this corresponds to actually being hitting the correct key maybe 77% of the time. It doesn't seem great, but it turns out that if you're doing that but typing faster, you get a better hit than if you get a better bit rate than if you were up at 95% and typing slower. So this corresponds to a tint of 60 milliseconds, causing the total trial time to be 250 after we add t-skip and t-rend. Question?
So given that it's just an 8-target
Yeah.
task, was there or if he gets it wrong, can he just move on and get more?
Yeah, so in this paper and in this task, there is no delete. That's something that we've changed in more recent papers that we've put out. And so this is just calculating more a theoretical bit rate. When you do have this delete key, you actually do want to be a lot more accurate because when we type on a keyboard, 2 selections to convey 0 information, right? Hitting a wrong key and then hitting the delete key correctly is actually pretty expensive. And so depending on how you define this bit rate, this curve here could change. All right, so we can also plot the theoretical line. So this little dotted line here corresponds to the maximum bit rate that you could achieve at that t-int. And so all this is saying is if your accuracy was 100% and you were integrating for the amount of time on the x-axis, then this would be your maximum bit rate. And we would expect that if we were to extend this line here and also extend this line here, they would eventually meet, because we would hope that when you integrate so much data, you would eventually decode at 100%. Does that all make sense? All right. So now we have what should be an optimal t-int of something pretty low, 60 to, let's call it 100 milliseconds, where our accuracy is not great, but because we're making selections so quickly, we actually end up having a higher bit rate. All right, so we're going to show you a video. And this video will now show you how we try to achieve these peak bit rates. And so what we did is we had a task where the monkey held the center target right here. And then we prompted the first target, which is to the left. This blue activity was his plan activity, which we then integrated. And then we selected the target, which is shown by the circle here. Immediately after that, we prompted a second target, which was up and slightly to the left here. And then we decoded the plan activity. And then we circled that target, indicating that we decoded that target. And then we planned another target, which was to the left. And so basically, this is a quick, rapid chain of decoder selections. And this is what the performance looked like. Sorry, let me play that again since I changed the volume in the middle of it. Did everyone get what they were seeing there? All right, I'll play it one more time. So you can imagine if you had a prosthesis like this would be pretty quick, right? You would be like, each of those selections could be like a letter. So like THE space B, and then ROWN. And so if you could do this, if you could have a prosthesis at these speeds, then you could type at a rate of about 10 to 15 words per minute, which is actually pretty good. So on your iPhones, I think the average person types at about 30 words per minute, or 20 to 30, but that includes things like word correction and word completion. So when you're typing on your iPhone, you're hitting the wrong key, but it corrects it for you. And so this is something that is a bit slower, yes, but can rival that in terms of the rate at which you can type. All right, any questions on that? This lecture, which we'll finish on Monday, you guys will actually see what this box is. For this box, in this lecture, it'll be something called a naive Bayes decoder. And that interpret neural signals box will say, OK, I saw these firing rates. And I'm going to predict that the monkey wanted to reach up and to the left. And so that's exactly what we want. All right. And so again, just at a high level, to show you the flow before we actually get into showing you a video of the decode and how we fit the decoder, we have a monkey. He is holding a center target. Oh, whoops. And then a target appears up and to the left. We've implanted our electrode arrays. Those electrode arrays are giving us the raw voltages on 100 different electrodes, or 96. 4 of them are ground. That's why we say 96. From this, we high-pass filter the signal to remove this slow, low-frequency potential, so we can draw a threshold to reliably detect the spikes. That threshold will give us multiple spikes on each electrode. And from there on out, we'll spike sort these different spikes. Then we're going to build the tuning curves, the heat maps that I just showed you. That's basically a tuning curve. We'll build a tuning curve for each of these neurons. And then across all the neurons that we have, we're going to be able to measure their firing rates. We're going to pass it to our decoder. We're going to decode then which target the monkey had planned to reach to. And then we're going to send that signal to the screen, and we're going to draw a circle around the target that he intended to reach. And so the circle denotes the intended target. And there are a bunch of studies that have used this approach, and they're here if you're curious of looking for further. And Krishna writes here, if there's magic, here it is. And so just looking at this, it might be difficult to actually see by eye what target he wants to reach to. In fact, I can't do it. But our decoders will be smart enough to handle this. And so we're going to show you a video now of this decoder in action. And so what you're going to see is the monkey is going to be performing a similar task to before. He's going to hold a center target, and a target is going to appear at one of the 7 locations. And then the monkey is going to plan to reach that target. And then we're going to decode that plan activity. And where we decode, we're going to draw a circle. And so if you see a circle appear around that target, it indicates that we decoded that target correctly. And then we're also going to interleave real reaches here just to keep the monkey reaching every once in a while. So that's a decode. We're going to reach, a reach, decode, decode, decode. Was that all clear to everyone? Nathan?
Are these directions, are you able to measure a magnitude?
We are able to measure magnitude as well from the plan activity. So the plan activity also has information about the speed and the distance of the reach that you're going to make. And so these targets, actually they may not have been equally spaced, but you can imagine a circle of targets at say 4 centimeters away, and then another circle of targets at say 8 centimeters away. And this is really good. We'll talk about this more in the next class, because if you have more targets, you can convey more information, right? If I have just 2 targets, I can only convey 1 bit. One target is a 0, and the other target is a 1. And if I have 4 targets, then I can convey 2 bits of information, right? One target is 0, 0, 0, 1, 1, 0, 1, 1. So the more targets, the more information I can convey per selection. But then what's the problem of putting up too many targets? Yeah, it's harder to, so if I put up more targets, then all of a sudden my accuracy is going to go down. Because now to differentiate between the target, say at 4 centimeters and the target at 8 centimeters, if this neuron cares more about direction rather than distance, then they might be hard to disambiguate. And so there's a trade-off there, and we'll talk about that. Yes?
So if he's supposed to plan but not reach,
Mm-hmm.
and if he chooses, like on these which the ones with the circles, and if he chooses to reach, won't he still get his juice?
So the task is very specifically designed such that if he reaches while this target, so for the BMI, for the neural decode trials, this center target was always there, and that's his cue that he's not supposed to reach. And so if he reaches while the center target is illuminated, the trial automatically fails, and he doesn't get juice. So monkey training is something that is very much an art, and it takes a long time. If you have really well-trained monkeys, you can get a lot of really good data. But and so training all these very specific things, there's a plus here. The monkey has to watch that plus with his eyes. And if the monkey's eyes move a bit, so if he looks at the target, the trial fails. And we're doing this so that it's not necessarily we're not decoding the eye movements to the target. We're only decoding his motor actions. his arm actions. And so there are all these very precise controls. And just to give you a sense of it, there are some tasks that we run in the lab that literally took a year to train the monkey to do. And so monkey experiments are very time consuming, but they afford this really unique opportunity to get really cool data. All right, so I'll leave off here actually because this is basically starting the parameter selection part of our discrete decoding. Are there any other questions about homework, midterm, this lecture? We have a minute, but if not, then you guys are welcome to take off. All right. Tushar, are they great? Do we enter the grades into Canvas? You have them? OK.
On the last video,
Yeah.
when it was said like the